So, how is everybody today? Okay, I'm seeing a lot of people come on saying good. I'm fine. It's a very good day today. Awesome. I am awesome. Super good and good. Well, I'm glad to hear it. My name's Jim Sauer, and I'm coming at you from the Kids Science Cafe here in Magdalena, New Mexico. We're about an hour and a half, 2 hours south of Albuquerque and the Atomic Energy Museum, which is hosting this STEM event today. Here at the Kids Science Cat, well, let's go back a little bit. I don't know how many of you people like Harry Potter, but in those books, in that book series, they like managing mischief. That's a spell, and whenever they cast it on the Marauders map, you can't see what's going on that map no more. Here at the Kids Science Cafe, well, we kind of like mischief. We kind of like getting in trouble. And what we do is we don't get to do this a whole lot in schools anymore. But what we like to do is we get kids interested with a very small lesson, and then we make you do it. For example, I might do a very small lesson on how to fly an airplane, and then I put you on a simulator to do that. And that's what we're going to be doing today. We're going to sit here and we're going to talk a little bit about asteroids, and then we're going to postulate what happens when an asteroid impacts with a planetary body. And then we're going to let you do it. Now, as I understand it, some of you guys are set up to do this demonstration yourself. And so we're going to kind of go through some of this and have a little bit of fun along the way. I'm going to share some content to get us started. So please bear with me as I push some buttons and stuff like that and get us all started. Asteroid impact, and then we're going to click a bunch of buttons right here to get us all started. And I am tickled that y'all joined us today. And here we go. So, as I kind of said, this class, which is scheduled to last 45 minutes and demonstration, is on asteroid impact. And this right here is a picture of an asteroid that has already entered into an atmosphere. We can see that certain portions of it are breaking off and going in different directions, but the main body is very much heading toward the center point of gravity. If this atmosphere that it was entering was planet Earth's atmosphere, it would be heading for the Earth's core, but it would be coming in at an angle. This right here is a buddy of mine. He's the one that got me kind of interested in what we call NEOS, N-E-O-S. And NEOS is a series of initials that stands for near Earth objects. Now, Dr. Klingelsmith here, you see his picture, worked for NASA for 30 years. And then he retired and moved out here to New Mexico, where he became the chair for the astronomy department at New Mexico Tech, which is in Socorro, New Mexico. He has an awful lot to do with the Magdalena Ridge Observatory, which consists of a 2.4 telescope, an optical interferometer, and then Langmuir Laboratory as well. He was also the president of the Astronomy Club, and every year he loved working with children. He has since passed on. He got a very rare form of cancer, and he passed away. But he is still here in spirit, and this was his experiment that we're going to be doing for you today. Now, we haven't forgotten Dr. Klingelsmith. What we did is when he passed away, because he studied near-Earth objects and asteroids and stuff, he had an asteroid named for him. Now, this particular asteroid behaves. It stays in the asteroid belt, which is between Mars and Jupiter and Saturn. His particular asteroid is 26652. And 3 days ago, this is where it was at. So as you can see, if we're looking across space with a telescope, a very powerful telescope, to see the Klingel-Smith asteroid, we would have to cross an awful lot of light and many orbits of other planets in order to see it. And right now, we'd probably have to be in the southern hemisphere as well. But here's a little bit of information about the Klingel-Smith asteroid. Now, asteroids, there's basically, three big types that you need to know about. There's the first one that's made of clay and silicate rocks. They're dark, and stuff like that. And then there's a stony type, which is primarily silicate as well, and it could have nickel and iron mixed into it. The last type, which is the type that we ought to be worried about most often, and you'll see why, is the M type, which is metallic. Those things can get very, very heavy, very, very fast. Now, I know that you ain't old enough, but you guys have seen my picture. I'm probably that old. The one big asteroid that hit Earth, geologists and astronomers think that this happened somewhere in the neighborhood of 80 million years ago. It struck land and water at the end of the Yucatan Peninsula. You can see where, we think there's a buried crater there. We have found remnants of the crater on land, and you can see that on geological maps and stuff. But this is the asteroid. When it struck Earth, this is the asteroid that got rid of all of the dinosaurs. And an interesting thing that you might want to think about as you stare at the ceiling or sit at a desk or a chair or something like that is what would have happened in terms of the development of other animals on this planet, the third rock from the sun. What would happen if the dinosaurs had not gone extinct? It's very possible that mammals, dogs and cows and people would not have risen to their place as what they are today if the dinosaurs had stuck around. So, I guess you could say that where asteroids hitting our planet is not a good thing, there are other things that we could consider that say 80 million years ago, it was a very good thing. Now, there is an asteroid, a meteor crater that you can go visit even today. This one is south of Holbrook, Arizona, and it's called Meteor Crater. It's about 3 miles. It's about 3 miles across, and you can drive up to it. You can get out. You can walk around it and stuff like that. This is a picture taken from a drone from above. If we got a little closer, you can see that hey, this was a pretty big event that happened, and from what we understand, it was an M-class asteroid. That means it was metal. And metal ones, as you might imagine, get very heavy, very, very fast. We think it was nickel iron. It was about the size of a Volkswagen Beetle. Now, we know that from Newton's second law that force is equal to mass times acceleration. We know that a Volkswagen Beetle can weigh about 2,000 pounds. And so that's the mass, that's the size of it. I say 2,000 pounds, and yeah, that's weight, but mass is a function of size and weight. And so if I dropped a Volkswagen Beetle, onto the ground from say 10 feet, it probably would damage the Volkswagen Beetle more than it damaged the road or the concrete or the rock or the dirt that I dropped it on. But there was something magic about this formula. This rock, this metal, that was about the size of a Volkswagen Beetle had speed with it too. And remember, Newton's three laws. I'm sorry if I'm breaking up. I'll see if I can speak a little slower and maybe I won't break up near as much. But at any rate, going back to the topic, we have Newton saying that force is equal to mass times acceleration. And anytime I multiply one number, one whole number, by another whole number, I get a much bigger whole number. So I've got a 2 with 3 zeros, and then I multiply that 2 and 3 zeros by, let's say, 25 with 3 zeros. And we know that 2 times 25 is 50. And now if I add, if I add 6 zeros to that, now my force in newtons is going to be something in the neighborhood of 50 million newtons. Not, and you know, that's a lot. And so this hole that you see in front of you, this crater, was made by a rock about the size of a Volkswagen Beetle, traveling somewhere around 25 or 50,000 miles an hour. And when it hit, all of that dirt left. It went into the air and it went into the lip that surrounds that crater, raising the ground and stuff like that. Now here's the kid kind of looking across that crater, and you get a bird's eye view then of just how, you know, how a little rock the size of a small car can scoop out a whole bunch of dirt and a whole bunch of rock, throwing it into the sky and throwing it around the state of Arizona. If it impacted the way I imagine, some of this dirt may very well have gone around the world. It would have gotten into the jet stream, and the jet stream would have transported as part of those high-speed winds. You can read more about Meteor Crater by going to Wikipedia. Wikipedia probably isn't the best reference, for this kind of thing, but it'll show you pictures. And you can visit this place and get an idea of what happens when an asteroid or a meteor actually impacts the Earth. We're going to stop the share now, and here we are, back to my pretty face staring at all of you. The next thing we're going to talk about for just a little bit is what you need to do this experiment yourself. You now know a little bit, just a little bit, about meteors and what we can do as experimenters, as scientists, and as engineers is that we can model the very same things. Well, I'm glad you think that's interesting. Thank you. We can model the same kinds of things on a smaller scale. Now, I've always wanted to do things on a big way. So when I do this experiment outside, I use a paintball gun. And I use real rocks and real sand and stuff like that. And I hit it with enough force that I can see when that paintball explodes, paint goes everywhere, of course. That's what it's supposed to do, right? But it also shows me something about the force vectors that the asteroid has on the side. But I also realize that maybe you want to do something that's a little funner and a little easier to do, maybe on cold winter days like today, where you can stay inside and do a little bit of work. But there's some equipment you need, because if mom and dad find out you do this and you make this mess, they gonna have something to talk to you about. Now, like I say, here at the Science Cafe, we like making messes and we like getting into mischief. But you need to be careful about mom and dad. You need to clean up your mess, and you need to do what you can to keep from making too much of a mess. So we're going to talk about some things that you're going to need along these ways. I'm pushing buttons again. So please bear with me a couple of minutes while we get to this. There we go. Okay, I want to talk about that one and that one and that one. I hope you all are having fun. I know usually we sit there and we go to me and a bunch of my buddies, we all pack up stuff and we get out there to the Atomic Energy Museum, and we let you guys walk up to us and let you play along the lines. Now, this is the back wall to my Kids Science Cafe. And I've got some stuff here that I think you guys need to know something about. So I guess the first thing I want to do is I want to annotate some stuff and point some stuff out to you to where you can sit there, you know, and get an idea of what you need to collect in order to have a little bit of fun. So here we go. This first thing that we're looking at right here is a tarp. It's a great big plastic thing. They don't cost very much. Your daddy probably has one out in the garage, and you ought to get one of them things. What that does is it catches the mess to where you can roll it up, take it outside, and squirt it down with a hose. The next thing that you're going to need a little bit about is I got this black tablecloth. I want a pen, I said. And I got a fancy one. This one's got the picture of the moon on it and stuff. And what I do is I put that over my tables that I push together. So I've got 2 plastic tables that I push together. I then got one of these turkey basting pans. They don't cost too much down at the dollar store. And I get some flour. Now, if your mama's going to be making cookies, you leave that flour alone. And if she wants to send me cookies, that'd be great. I'd love to have cookies. I also need some cocoa. I like chocolate cookies. All right. So I'm going to erase all of this now so that I can get into this and show you some more stuff that we're going to need. Going back to the pen again. You'll notice that I've got a little sifter thing. I put cocoa in there and I'll show you what that does in just a minute. I've got a scale because me being an engineer and a scientist, I like to take measurements. And then I've got my rock samples. These are my meteor samples. And I picked different kinds of rocks, like this one right here. I'm going to have to erase again. This one right here is basalt. It's old lava. And while it's sharp, it's not very heavy. And then, going back to my eraser to get rid of that, the next one that I got is that second type of asteroid, which is silicate material. It's gray. And then this last rock I've got is metallic. There's a lot of iron pyrite in it and stuff like that. And I'll get those rocks and show them to you in just a couple of minutes. We'll pull them up to where you can see them on the camera. Okay, so those are the tools and the equipment that you're going to need to do this demonstration. In the background, last item, you'll see that I've got an old chemistry set clamp that's holding on to a meter stick. And this is so I can measure how high to drop my sample asteroid from. So that right there is pretty much everything you need. You can use all of it or only some of it. To tell you the truth, the only thing you really need is the turkey pan, flour, probably the cocoa, the tarp, and then some kind of black plastic or black cloth, tablecloth, so that you can make some measurements and stuff like that. All right, so let's get down into some serious business then. See what we can do from there. And next slide. So here's my tables. You'll see that my tarp is underneath the tables so that I can catch all of the dust from the flour, which is going to simulate planet Earth's dirt. I put my tablecloth on top of it because I want to see where Earth's dirt moves to as I drop asteroids into it. Here I begin the setup of my turkey pan and my meter stick. I then begin pouring flour into the turkey pan. Here's my cocoa. I put the cocoa in the sifter and I sprinkle it on top of the white. Now, what this does is we could sit there and say the brown cocoa is the very top layer of dirt. But what's really nice, and you'll see this when we do the experiment, the white stuff is what we call ejecta. And when a meteor or an asteroid hits the surface of Earth, the ejecta is all of the dirt that is scooped out and thrown out. And this allows us to model and see where the dirt went. So here it is. We're at a ready state to sit there and start dropping some asteroids. Here's my 4 asteroid types. On the far left, you see the basalt kind of rock. It's light. It's got a lot of air pockets. Oh, Hunter, it is a lot of fun. And like I say, anytime you can make a mess, it's even more fun. This right here is a silicate kind of rock. This is a silicate kind of rock with metal mixed in with it. And this is a metallic kind of rock. In fact, if you look carefully at the end of my arrow, you might be able to see a cubic form, a shape, and you see these little square shapes. That's actually iron pyrite. And so if I was to show you what the weights of certain are, this is the lightest weight. This is the next lightest weight. This one right here, this is the heaviest one. And this is next to the last in terms of heaviness. Time to erase all this happy stuff. Next time, I'm going to use a computer and not my tablet. All right. So here's where I begin weighing my samples. I've got a regular kitchen thing. You'll notice that the lava, the basalt, weighs 14 grams. And I guess that's the end of that. So let's stop the share. And let's go back into, let's see why I can't see all of the shares that I had, all of them wonderful pictures that I took. Oh, all right. Now I see what's happened here. Well, that wasn't very nice. So at any rate, without any further ado, I could tell you that our second sample was 71 grams. And our heaviest sample was 132 grams. Now we know that there's, something like 545 grams in every pound. So all of these things weigh less than a pound. So now what we're going to do is we get to play. We get to make that mess that I was talking about. I'm going to switch my screen around. And what you should see now is my experiment table. You should see everything set up. You should see 4 samples laid out in front. You should see the scale there. And in a minute, you're going to see my ugly mug walk around this way and start talking to you from over here. We're going to get the scale out of the way. Now, this right here, we said, was the lightest of all materials. It's the basalt. If I took my ruler to it and used the metric system to measure it, I could tell you that this is about 3 centimeters by 2 centimeters, okay, by about 2 centimeters. So 2 times 3 is 6, times 2 is 12. So we could say roughly that this was, 12 centimeters in 3 dimensions. We have our experiment here. We're ready to go. I'm going to drop this from about 1 meter in height, and I want you to focus down here at the bottom as she comes rocketing in. Here we go. In 3, 2, 1, mark. There's our first impact. Now, the nice thing about these things that we call smarty farty phones, an awful lot of these things now have a slow-mo feature. So one of the things that maybe you could do when you do this experiment is take your slow-mo feature camera, have one person drop it, and then you focus down here and get a slow-mo, because that explosion is very, very cool. Now, it happened very fast, but what I want to point out here is we had ejecta that came all the way over here. We had ejecta that came from here all the way to here. We had ejecta that splashed all the way out to there. And getting those measurements, imagine this is dirt, okay? And we know that this is only a couple of centimeters in terms of size, but if I looked at how far that thing went, this thing went 60 centimeters. And that's just for a little dinky 14-gram kind of thing. We can also measure how deep it went, okay? It went down about 3.5 centimeters. We could measure how much in diameter it is. We said that this thing is only 3 centimeters wide, but it made a crater that was 6 centimeters wide, okay? It went 5 in that direction. So all of this stuff gives us a little bit of information about what happened. And see, I told you that we used cocoa to make it brown, and you can see all these white little polka dots along the top where this ejecta came out and spread out. And we can see that this isn't flat anymore either. We can reach down, we can pull that rock out, and experiment 1 is done. And all you do is you take your little ruler or whatever you got there, you flatten it out nice and neat, okay? Then we sit there and we get the cocoa. We put a little bit of cocoa inside this screen. And then all we do is we tap it and we recock the experiment. That means we set it up to do experiment 2. And this time we're going to be using something that's even bigger. The ground has now been returned. Now, we're not completely set up for the next experiment because there's something else I've got to do as well. I've got to erase all of the ejecta, marks from the table and all. I want to get all that erased so that new ejecta shows up. Now, I should have taken out my smarty farty phone and taken a picture of this whole thing as well, maybe with a ruler laid into it to where I could get measurements and that sort of thing. You can make this as much like an engineer's diagram or notebook, or you can sit there and make it just simple, making a mess like what we're doing right now. All right, so now I've got a stony silicate rock. I can give you the exact weight here on the scale. This one is 32, so this one was 16. This one, even though the size is about the same, this one is more dense. And so if we look at Newton's law, force is equal to mass times acceleration. We know the mass is 32. We know that gravity falls at 9.8 meters per second squared. I'm going to drop it from 1 meter. And so I ought to make more ejecta, and I ought to make a bigger hole. At least that's my hypothesis. So let's give it a try. Here we go. In 3, 2, 1. All right. This time the ejecta came primarily this way. it went all the way to where my hand is right here. Shoot, if I look at that, that's 15, that's 30, there's 45, that's nearly 60 centimeters away. Now the ejecta path on this one only went about 15 centimeters, but nonetheless, it gives us an idea of what happens when an asteroid impacts the Earth. We can see the ejecta pattern on the top and how there was an awful lot of lit building right here. And so if we measured how far this went down nearly 6 centimeters, which was more than the other one. The size of this is 7 centimeters that direction and 6 centimeters this direction. So our hypothesis, more or less, was correct. This had more mass, and so it made a bigger hole. There's experiment 2. Again, we go to recocking this by making it all nice and flat again. Now, the Earth's surface isn't perfectly flat, but for the purposes of this experiment, so we understand something about craters and how craters are formed and stuff like that, well, starting out flat is probably a good way to go. Always adding a little bit more cocoa. Kind of get back to our dirt and stuff again. Get my eraser. Now, if you get Mama's Swiffer and you use it to erase this, you need to replace this thing too. Because the next time she goes to dusting, or your daddy, or whoever it is that does the dusting in the house, they're going to put flour all over the place. And then they're going to probably call your name with a little bit of anger. And you don't want that, I promise. Okay, so here's our third sample. This is the metallic rock that has a lot of the iron pyrite in it. I'll see if I can get it up there kind of close to you to where you can see some of the metal fragments in this. All right. This one, we know that the first one weighed 16, the second one weighed 32. This sample weighs 74. So we're doubling it about every single time we go up. So I ought to have a bigger hole. My ejecta pattern ought to go out a lot farther. And it really depends upon which way this thing is oriented as to what my ejecta pattern looks like. And we know that it's going to rotate a little bit as it falls from 1 meter. So here we go. In 3, 2, 1. Now, can you imagine what that looked like, you know, in slow-mo? Look at this perfect circle right here. Some of that came out, and you know, we've got this rather interesting hole going in. If I measure this one is 8 centimeters by 9 centimeters. And all of that dirt that was there went out everywhere else. An awful lot of it came out to here. I know that there's a small ejecta pattern that came in here. I've got other small ejecta patterns that came out this way. I got a beautiful ejecta pattern right here on top of my soil. But almost nothing landed over here. And again, that's because of the way this thing landed. This thing landed with a big flat side down. The angled sides went a different direction. So we cover it all up. Now my hands are getting real dusty right now, and everything's being slippery because of that. So you need to be careful and take your time so that you don't make any bigger of a mess than what you already have. I know when Miss Diana gets down here to see the mess I've made in the Kids Science Cafe, I'm probably going to be in a little bit of trouble because this flower is going to be all the way on the other side of the room. And Miss Sauer is going to be saying, you need to vacuum this place, get busy. So here's our metallic asteroid. It's much heavier to my feel, and it weighs 102 grams. It's got very sharp angles, and I can see crystalline structure in there, but it does feel very, very heavy. Here we go. For 1 meter. In 3, 2, 1. Look at the big pile that landed right here. Little bits and spews on the other side. I still have more or less a circular area. If I get some measurements on this thing, it's about 10 meters lip to lip on the crater, this direction, and it's 11 centimeters in this direction. And it's about 6 centimeters deep is where the top of this guy sits. But if I pull him out and look at how much he sunk down, he's about 8.5 centimeters deep is where he stopped traveling. Force is equal to mass times acceleration. Remember that. Newton's second law. It's the multiplication problem for the math and stuff like that. So, y'all have any questions? You want to use a bigger rock? But are you sure? Okay, let's do a bigger rock. So this one's metallic, and this one's one of them flat rocks that you probably skip across lake water. Which one you want to use? You know this one's going to throw crap all over the place, right? Boy, you guys are wanting to get me in a lot of trouble. And you want me to try and make it to where the flat side hits, not the skinny side. You need to come to the Kids Science Cafe. We can have fun. Here we go. In 3, 2, 1. Oh! Look at me. I got ejected on my good shirt. There's flour all over the place. Look at this. There was flour that went all the way down here, all the way to the ground. There was flour that went all the way back. Look at this ejecta pattern. It went, oh my goodness. I'm going to need more than a vacuum in here. I got ejecta all the way on this side. You can see it on my pants and shirt. I got some ejecta here. There's a big path of no ejecta right here. There's some ejecta here, but look at all of this ejecta. Look at all this earth soil that went off here and then down onto the floor. Oh man, I'm in a lot of trouble now. I don't know who gave me that idea, but they ought not have done that. Okay, my ruler says that this crater is 14 centimeters wide one direction and 12 centimeters wide in another, and then 6 centimeters deep. Now, if we wanted to know something about how much dirt that was, some of you if you've done 5th grade math, you know that all you really have to do is look from the top here and say, okay, that's 13. You take 13 and you multiply it by 12. 12 times 13. And then you multiply that by 6. And that gives you the cubic dimensions of the soil that was thrown out of here. Okay? All it is an answer to a multiplication problem. And from that, if we weighed how much flour weighed, a certain size, like something, if we took a measure of 1 centimeter by 1 centimeter by 1 centimeter, which would be 1 cubic centimeter, if we weighed 1 cubic centimeter of flour, we would know how many cubic centimeters we'd have by that multiplication problem. And then we could model how many pounds or how many tons of earth a scale shot was with respect to our asteroid. That's quite a hole. That's quite a mess. I don't think I want to clean up this mess. Can somebody send a maid down here? 202 Spruce Street, Magdalena, New Mexico. So, ladies and gentlemen, that pretty much concludes our demonstration for today. I'm going to share with you a couple of more pictures to show you close-ups of what these craters looked like. Here we go, sharing content one last time. Going to our asteroid impact file. And here we go. So again, here's our 4 samples. The one that made, not including that big flat one that we just dropped, okay? We can see that our heaviest one is the 3rd one in. This is the basalt, which weighed 14 grams. And this is a close-up picture of the crater, okay? You can see the crater rim right in here. We can see little bits of ejecta patterns that went out this way. We can see that one big ejecta pattern came all the way out into the black cloth above. We're going to erase this now. I think we're going to erase it. And go to the next slide. Here I've laid the ruler down in front of the crater to give you an idea of, the size of the crater from rim to rim. And you can see that there was a little bit of shape added. I'm going to show you connotation-wise where that shape came in. You can see that it's flat here, but then it goes up. And it was pretty flat here, but you can see it goes up. And there's this crater in the middle that goes all the way around in a circular pattern. This was the next crater, and you can see there wasn't very much ejecta or anything in this one experiment. In fact, even though it was more dense, the hole was much smaller and there wasn't very much ejecta. I mean, you can see, small ejecta patterns like this one right here, but by and large, there wasn't very much ejecta out of this experiment that was done a couple of days ago. Going to the next slide. Here's our 71 gram sample, and that was the one that's got a lot of, iron into it. And you can see that that one was a whole lot more different than others. And it's got some very nice ejecta patterns, especially this one right here and this one right here. You can even see a very prominent one that goes up into this direction along these lines. You can see, you can't even see that asteroid. It's completely sunk below the surface of the Earth. So scientists and engineers and astronomers and geologists would work very, very hard getting that out of the dirt. Here's our 100-gram sample. And you can see that this one is just a mess. Dirt, soil, everything went everywhere. And what's really kind of nice here is we see this part right here. It's made a very sharp dig all the way down. And then we've got our ejecta patterns that tended to go a little bit of everywhere. It was just a mess. I like this one because it's almost a straight line going in that direction right there. And that gives you an idea how deep it is where you make those measurements and make notes. Here's a picture looking down. You can see him sitting down there in the very bottom of that. You can almost see the uplift that has occurred in this area right here. This area right here, and even an uplift along those lines. And the panelists sit there and say, I need to shut up now because I guess I'm taking too much time. I am so very sorry. It is past my time. Boy, 45 minutes goes when you're having fun. I thank you all for paying attention. If there's any questions, you want to come down, give me a holler. I'm at 202 Spruce Street in Magdalena. We meet every Friday. Goodbye. And I thank you very much. I'm glad you thought it was amazing.